Hi, this is Margo. This is Sunday afternoon, December 15th, 2019. I hope everyone is doing well. And we're going to look at methane today. We're going to look at the CAMS data. They just put up the data from yesterday, Saturday. We're going to look at the NOAA data. I also have a paper that I'm going to present today that explains why we see such high methane releases around the edges of the coastline in the Arctic in the wintertime. We don't see this, or we didn't see so much over the summertime, and then as soon as it starts getting dark up there and colder and the sea ice starts coming back, we're seeing higher methane releases. So this paper talks all about that. It has just been published. So we're going to look at that. We're going to look a little bit at CO2, and we're going to look a little bit at Sam Carana's chart on predicted rising temperatures. So we're going to start just by looking at the map here. This is Copernicus Atmosphere Monitoring Services out of the EU methane forecast. The latest data is from yesterday, Saturday, December 14th. We're looking at the Arctic view and surface level. And what we can see here, this is the Arctic view, so the North Pole is here, right here in the center. This is Greenland, here's Canada, this is all Canada here. This is United States over here. This is Alaska. This is Siberia, which is Russia. This whole area is Russia. Comes all the way across. It's a huge area. Takes up most of the coastline on this east side. This island is Novaya Zemlya. We talk about this island in this area a lot. Right here is the Yamal Peninsula. This sea in between Novaya Zemlya and the Yamal Peninsula is called the Kara Sea. In the wintertime, we see high releases of methane coming up here. To the west of Novaya Zemlya is called the Barents Sea, not the Bering Sea. The Bering Sea is over here with the Bering Strait, but this is the Barents Sea. And we see high releases of methane over here too. And the paper, we're going to be looking at concentrates on this area. And also, it talks about this area around Svalbard, which is right here. Greenland is here. And about high releases of methane to the west of Svalbard, which we see releases right here. Over here, this is the Laptev Sea. And over here is the Chukchi Sea. So, and over here by Alaska is the Beaufort Sea. So, that's just to get you oriented for these areas that we're going to be talking about in the paper, and we're going to come back to our methane report once we look at this paper. And I think you'll have a new appreciation for what we're seeing over here. This paper was published online December the 9th. It was published in Advances in Polar Science. This is out of China. The authors are not Chinese, but this peer-reviewed journal is out of China, and I'll leave the link below. Robin Westenra sent me this article. This is the Google Docs, Google Drive, where you can find the article and read it, because this website, Advances in Polar Science, where it's actually published, and you can see it, it's in the current volume for December 2019. Sometimes you can't get to their website. I just tried just now and it's down for whatever reason. So the title of this article, we're just going to hit the highlights because it's pretty scientific, but I've read through it, and so it's called Methane Increase Over the Barents and Kara Seas After the Autumn Pycnocline Breakdown, Satellite Observations. So let's just go over the title again. Methane Increase Over the Barents and Kara Seas. So Barents Sea is here, Kara Sea is here. So that's what we're looking at. After the autumn pycnocline breakdown, satellite observations. Well, what does that mean? Autumn pycnocline breakdown. Well, I looked up pycnocline, and on Wikipedia, pycnocline is the clean, and I don't know if I'm saying that right or not, but that's what I'm saying. So everybody just got to deal with it. Or layer where the density gradient is greatest within a body of water. An ocean current is generated by the forces such as breaking waves, temperature and salinity differences, wind, Coriolis effect, and tides caused by the gravitational pull of the moon and the sun. In addition, the physical properties in a pycnocline driven by density gradients also affect the flows and vertical profiles in the ocean. These changes can be connected to the transport of heat, salt, and nutrients through the ocean, and the pycnocline diffusion controls upwelling. Below the mixed layer, a stable density gradient, or pycnocline, separates the upper and lower water, hindering vertical transport. This separation has important biological effects on the ocean and the marine living organisms. However, vertical mixing across a pycnocline is a regular phenomenon in oceans and occurs through a shear-produced turbulence. Such mixing plays a key role in the transport of nutrients. Now let's apply what we just saw there to what we're talking about here. So they're saying that a pycnocline is a layer of water that's denser in the big body of water. It's like a layer of water that's denser, and it separates different areas of the water or of the ocean. And so if you have a layer that's denser, it can help block off, for instance, here in the Kara Sea or the Barents Sea, if you have a dense layer in the middle of the ocean or the water there, and you've got methane trying to come up, if the water is dense, it can hold that methane in and keep it from coming up through the other layers. So that's when you have the pycnocline. But if there's a breakdown, like what this paper is talking about, the autumn pycnocline breakdown, it means that that layer is broken down, and so you can have mixing in the water and also higher releases of methane. So that's the bottom line to this whole paper. So this paper was written by these three guys, Leonid Yurganov, Frank Muller-Karger, and Ira Leifer. And Professor Yurganov is out of the University of Maryland, Baltimore County in the USA. Dr. Muller-Karger is out of the University of Southern Florida, St. Petersburg, USA. And I guess as Dr. Leifer is out of Bubbleology Research International, Inc., Solvang, California, USA. So all these guys are from the United States, and we're going to look at this. And you're going to find this interesting. I'm just going to read the abstract, and then we're going to go through some highlights of the paper. 7 operative thermal infrared, or TIR, spectrometers launched at sun-synchronous polar orbits supply huge amounts of information about Arctic methane, or CH4, year-round, day and night. TIR data are unique for estimating CH4 emissions from a warming Arctic, both terrestrial and marine. This report is based on publicly available CH4 concentrations retrieved by NOAA and NASA from spectra of TIR radiation delivered by EU IASI. Now that's the NOAA data that we look at, and US AIRS sounders. Data were filtered for high thermal contrast in the troposphere. Validation versus aircraft measurements at 3 U.S. continental sites reveal a reduced but still significant sensitivity to CH4 anomalies in the troposphere below 4 kilometers of altitude. The focus area is the Barents and Kara seas, BKS. BKS is impacted with warm Atlantic water and mostly free of sea ice. Yes, we know that, and when we see the sea ice, it's not very much, and it's not for very long. It is a shelf area with vast amounts of oil and natural gas and about 90% CH4 or methane, as well as methane hydrates and submarine permafrost. Although in summer, AIRS and IASI observed no significant difference in CH4 between BKS and North Atlantic, a strong monthly positive CH4 spatial anomaly of up to 30 parts per billion occurs during late autumn to winter. One of the explanations of this increase is a fall-winter pycnocline breakdown after a period of blocked mixing caused by a stable density seawater stratification in summer. Enhanced mixing lets CH4 or methane to reach the sea surface and atmosphere. So that's what I just told you guys. So that's in the scientific terms. So what we're looking at is right here, like in the Kara Sea, these high release, and even the yellow is a high release because we're looking at 2020 up to, so this yellow green thing right here, that's about 2020 parts per billion, and up into this dark brown is anywhere between 2160 to 10,000 parts per billion. So when you see, like this chartreuse is 2000, like this, well, it's hard to tell. It could be this color, I don't know, but once you get up to 2000 and higher, you're really getting up there, and you can see differences in the colors of the green, and the lighter green signifies a higher release of methane than a darker color of green. So what we're seeing at the beginning of Saturday or the end of Friday, we're seeing increased amounts of methane releasing all across the Arctic here, and here's the Chukchi Sea. It's releasing. We can see the changes in the colors of the green, but specifically Here's the chartreuse color coming up, more yellowy. And then here, north of Canada and Greenland, and then here between Svalbard and Greenland, and then here in the Barents Sea, and then here in the Kara Sea as well. So let's go back to our paper. So they're saying that it's because of a breakdown of this stable layer of water, the pycnocline, that was fairly stable in the summertime, but then once winter hits, and in the paper they talk about how it's the difference of the temperature, water temperature, from the cooling effect that causes the breakdown of the pycnocline, or the stable layer, which allows for the methane to come up. Even though it's colder weather, we're talking about what's coming up from the sea floor. And so that's why it's more in the winter than in the summer. Because I always wondered that. I didn't know why. It didn't make sense to me. Alright, so we're going to read through some of this. Here's the introduction. The Arctic has experienced the fastest warming on Earth over recent decades, termed Arctic amplification, with the Arctic Ocean warming at nearly double the rate of the world's oceans. I'm going to pause for a minute. By the way, for people who are new to my channel, if anyone tries to troll my channel, or you're a climate denier and trying to troll, your comments are not going to be approved. This place is not for climate deniers. Alright, I just had to get that out of the way. Now, I think that we have lots of different things going on just besides abrupt climate change. But we're focusing right here, right now, on the science of abrupt climate change. That's what we're focusing on. And so anyone trying to come in and troll, their comments are not going to be approved. And people who have been watching my channel for a while already know that that's the rule. And, you know, if you want to troll, you need to go somewhere else. This is not the home for it. Due to Arctic warming, there is concern that the vast stores of the important greenhouse gas methane, or CH4, in hydrates, permafrost, and other valuable reservoirs can be released to the atmosphere. The relative impact of CH4 is second after carbon dioxide on century timescales and larger on decadal timescales. Warm Atlantic currents make the Barents and Kara Seas, or BKS, climatically important with respect to instability of seabed CH4 due to the input of warming seawater. So what they're talking about is this area here with the Atlantic, with the water coming in, it's getting warmer and warmer and warmer, and so as it comes in and mixes, then it starts melting all those hydrates. Then the methane is released. The Barents Sea is a shallow shelf sea, average depth 230 meters, with depressions to 400 meters. It currently is close to ice-free year-round. The Kara Sea is even shallower, an average depth of 100 meters, and ice-free in summer. The BKS has extensive proven oil and natural gas deposits, the latter of which are primarily CH4. Although rather limited, existing data show these reservoirs drive CH4 seepage into the water column. At depths greater than 250 meters, CH4 forms hydrates that are stable in the cold BKS deep waters about 1 degree C. Additional seabed CH4 is sequestered in the Kara Sea and the South Barents Sea as submarine permafrost. Warming seabed water may destabilize submarine permafrost and hydrates, although specific mechanisms and timescales are uncertain. So they're talking about, here's the Barents Sea and here's the Kara Sea. Oh, and also all this area is radioactive from all of the nuclear bomb testing that was done in this area and on Novaya Zemlya during the Cold War. And I did a whole video about that in whatever year that was, I forget. Most sea bubble CH4 dissolves in process of ebullition in deep water where methanotrophic bacteria oxidize it on weeks to years timescales. Only a small fraction of the sea bubble methane directly reaches the air. The seasonal summer pycnocline prevents vertical turbulent diffusion of methane with concentrations near the seafloor that may be extremely high. So they're saying that in the summertime, that layer of water holds the methane down to the seafloor, and it can be a high amount that holds it down, that doesn't come up. They studied dissolved CH4 concentrations to the west of Prins Karls Forland, or Svalbard, in August 2010, not in winter, and found that CH4 bubble plumes dissolved below the pycnocline and were not vertically mixing to the upper water column. They suggested that during winter, in high latitudes, after the summer stratification breaks down, vertical transport of CH4 from the bottom layer is not limited anymore, and CH4 can reach the sea surface. The most comprehensive CH4 measurements at the seafloor and in the atmosphere in the region were collected to the west of Svalbard in June and July 2014 by Meyer et al. They found that summer CH4 release from seabed sediments substantially increases CH4 concentrations above the seafloor with a sharp decrease above the pycnocline. They suggest that dissolved methane captured below the pycnocline may only be released through the atmosphere when physical processes remove the pycnocline as a dynamic barrier. So they're talking all about this pycnocline as this layer of water that's acting as a barrier, holding the methane down, and once that layer is removed, then it comes up. So that's why we see it higher in the wintertime. So I'm gonna fast track through here now. Then they start talking about satellite observations. Oh, here's Shikova, Natalia Shikova et al. 2010 investigated summer and winter methane flux from the East Siberian Arctic Shelf, or the ESAS, encompassing the Laptev East Siberian Seas and Russian part of the Chukchi Sea. More than 5,000 at-sea measurements of dissolved methane have been collected. Greater than 80% of ESAS bottom waters and greater than 50% of surface waters were supersaturated with methane regarding to the atmosphere. So they investigated summer and winter methane flux. In summer, diffusive and ebullition fluxes were estimated respectively at, and this is all scientific, I can't read all that. And in the winter, it was 7.72 and totally 10.64 TG, whatever. So it was a lot higher. It was like 9 or 10 times higher in the winter time, it looks like. It was a lot higher. Satellite observations are extremely useful for characterization of Arctic CH4, especially over open sea, due to their continuous and global data record. Thermal infrared, or TIR, CH4 data are available globally day and night, whereas SWIR CH4 instruments are ineffective in the Arctic due to low or no sunlight, low reflectivity from water and ice, and long atmospheric optimal path. TIR orbital sensors include AIRS Aqua, IASI, METOP A, B, C, and on and on and on. It's a whole list. And anyway, they tell what all they take. CH4 retrievals for AIRS and IASI are publicly available. Yurganov et al. 2016 suggested a filtering technique for the Arctic data and presented data on seasonal, spatial, and interannual variability of methane in the layer below 4 kilometers. They concluded, quote, seasonal increase in methane has been observed since late October to early November. This can be associated with the beginning of vertical convection in the ocean caused by the cooling of the surface layers and the simultaneous increase in temperature of the underlying water layers. Bottom layers saturated with methane are brought to the surface. Unquote. So that's what the whole paper is about. So as the sea surface cools, the air cools, sea surface cools down starting October, November. When it gets dark up there, then we've got the warm water coming up, and so that pycnocline layer is not there anymore, and so now the methane can come up. And it was trying to come up all along in the summertime, but the pycnocline was holding it down. So that's the bottom line. So let's go on. So they talk all about their data and how they look at it and take it in. And here's their charts for the different satellites and lower tropical, upper tropical, etc., etc. And we can see it going up. They're all going up. So now I found these images quite interesting. So here's the satellite data from the IASI, and this is month by month in 2018, so this is last year. Now here it is in January, and we can see the red over here in the Barents Sea, and also down here by Greenland. I'm having a brain fart, I can't remember that bay. anyway. So here by Greenland again, it's really high. Here it's really high in March. Over here, oh, I've got to see what that is. I know. Oh, Baffin Bay. That's right. I'm sorry. Having a senior moment. Baffin Bay was red over here. Here we are in the BKS again. Really red for March. And then you look at April. How it starts going down. Going down, going down. And so as the northern hemisphere starts warming up, then the methane release starts going down from the Arctic region. And I didn't understand why that doesn't make sense in my mind. In your mind, you're thinking, well, it should be coming up. But no, it's because of the pycnocline. I'm so pleased to learn all of this. Thank you, Robin, for sending me this paper. This explains a lot. Here's May. Here's June, July, August, and then in September, and we're starting to get a little bit of red up here in Canada, as you can see. Here in October, it's spreading out over the Arctic. So we're seeing the methane coming up. And then November, look how red it was in November. And I was reporting on methane last year. I've been reporting on methane for almost 2 years now. Well, about a year and 3/4. So November was the highest, and then December, see how it moved on down over the ocean, the land here. Here's the BKS, here's the Baffin Bay. And these are parts per billion. This is from 0 to 4 kilometers. So it's from the surface down 4 kilometers. So up to 2,000. And this kind of, this blue is 1850. Then this kind of blue-green is 1900. This orangey red is 1950. So we can see a huge increase from summertime. It looks like around between 1900 to around 1920 or 30 in the summertime, and then it starts coming up, getting more yellow in September when it starts cooling down up there, and then getting into the reds. So up into the red-orange 1950, starting in October, and getting on up into 1980 up to 2000 by November, December. Then January was a little bit lower. Here's February, March, and April, and then May was when it's at its lowest. So that explains a lot. So that makes sense to me. So I hope people find this interesting and informative. And here they do a breakdown. Here's just this BKS area. Here's Norway. Here's Novaya Zemlya. Here's Svalbard. And here it is. The difference when they go from the lowest to the highest. So there you have it. Conclusions. Satellite measurements of CH4 concentration in the lower 4 kilometer of the troposphere reveal a significant up to 30 parts per billion monthly anomaly referenced to North Atlantic maximized in November, December, January over vast areas of BKS as well as part of the Greenland Sea. Okay, so it's not down into the ocean 4 kilometers, it's up into the atmosphere. So it's the lower troposphere. So it's surface level is what they're looking at. Satellite observations show similar but less pronounced anomalies in autumn-winter over other Arctic areas. This CH4 anomaly may be interpreted as intensification of CH4 flux induced by turbulent diffusion and or convection after a breakdown of the summer stratification, or pycnocline. After a confirmation of a significant wintertime flux from Arctic seas by direct measurements, the methane CH4 emissions may be included into the methane budget. So we got to add that to our methane budget. And here's all the abbreviations in case you don't know what they are. You've got to have your own dictionary to know what all that is. And there are all the references. So I found this paper very, very educational, very helpful, and now we can understand more about why we're seeing higher releases of methane in the Arctic in the wintertime than in the summertime. So we're going to leave that. And I'll leave the link below for the Google Docs so that scientifically minded people can read this. Alright, now let's get on with our methane report. So now that you understand that, know that this is why we're seeing these higher methane releases in this BKS, Barents and Kara Sea, BKS, and also over here to the west of Svalbard. Now look over here in the Chukchi Sea and also in the Laptev Sea we're seeing higher releases. And this is coming up through the sea ice. There is sea ice there. It's not very thick, but it is there. We're not going to do sea ice today. We're not going to look at climate reanalyzer. We're not going to do any of that. I really wanted to focus on that paper so that we could understand what's going on. We also are seeing these high releases through Siberia, and this is like continuously going off, and it goes off in waves. Look at this building. So the data is for Saturday, and forecast runs Sunday through Wednesday. So we can see this is coming up into the atmosphere. It doesn't have to be summertime. I was always thinking summertime would be the time for the blowout, but I'm of a new mindset now that I read that paper. So now let's take a peek at North Pole view. This is the pretty much the whole northern hemisphere. Let's load this up. It's got to take a few minutes to load up. We're seeing huge releases here in the United States where we had all that rain and snow. Here's China. This is in northern India. It's also releasing out of the ocean here. We see now that paper focused on the Arctic, but we also see high releases of methane in the sediments around coastlines. That's another area we see huge releases. Look at here in the Indian Ocean. That's humongous releases coming up. We've got high releases in the Atlantic Ocean off the East Coast. We've got high releases over here off the west coast of California. And it's all over the place. See over here from now here's the Kamchatka Peninsula in Russia. This is Japan over here, Japanese islands. That's all Japan. So if we have a blowout or such an increased amount of methane release in the winter time, it's going to dump a lot of moisture, or it causes the atmosphere to heat up so that we have more moisture being held in the atmosphere. So we have bigger snowstorms, we have these atmospheric rivers, we have more flooding, and then it also raises the CO2 levels. It's CO2 equivalent. We've talked about that. And so that will make next summer that much hotter. So we really don't have much time left. We really don't. I've been really pondering this about, how much time do we have left? And, real sensitive to that right now, especially since my friend died in September. It's been 3 months, and just going through a few boxes of his stuff, but and I'm decluttering my apartment and decluttering my storage unit, and it's like, why do that if there's so little time left? But it's so I can be ready to leave the planet. Because it's like bringing up my whole past and the whole life review. So it's forcing me to deal with things that I kind of ran from, and I've been so busy going from one thing to another, and from career to a career, and people and relationships, and taking care of people and different things, that I haven't really spent that much time just on me. And so I'm taking this time to do that. So that's kind of another reason I don't do a lot of videos right now. But I recommend if you want to get ready to leave the planet, start decluttering. So what if we're all going to die within the next 2 or 3 years, or 4 or 5 years, whatever? It's It's, you know, where are you spiritually? Are you ready to go? Are you ready to leave? Alright, so there's the global. Now let's go. And best way to get ready is to do a live review, and best way to do that is to go through all your stuff, because trust me, you'll find stuff you totally forgot about. And it's painful, I know, but you need to do that to be ready. We have to refresh this to get the right chart. So here we are at 500 HPA, or about 18,000 feet up in the atmosphere, and we can see that methane gathers in the colder regions. That's where it's more dense. Where it's colder, that's where it gathers. That's why you see it all around the Arctic there. But it's also coming down, see, through Europe and Mediterranean, coming down over India, coming down here, and so on. And then if we look at total column, this is going to flip you out. It's been flipping me out. What we're seeing, okay, let's refresh. This is all the methane added up through the layers for the total column. So this brick red is 1900 parts per billion. The dark brown is 1920 to 2320 parts per billion. So this bright red is 1880 to 1900 parts per billion. So we can see that the higher levels of methane are coming up through the columns and spreading out over the globe. So if we just look at a couple of different views, if we look at Eurasia, can see a lot of areas are popping up the higher colors. And orange, orangey red, orange is 1860. So those higher readings are really popping up. If we look at the Pacific view, we can see this orangey red is moving across the Pacific. We also can see higher over North America, and look at the red right up here on the US-Canadian border. If we look at North America, right here, and then down here in Southern California, it's really high for total column. So it's definitely getting worse. As it's spreading out. Where was I? What was I going to show? Oh, we'll just go back to global. Now, let's look at the NOAA data. I took the NOAA data from yesterday. I'm going to try and keep up with this on a weekly basis, especially during the winter time, now that I know that this can be a time when we really have to watch this, where it's really increasing over the Arctic. Even though it's increasing over the Arctic, it's going down so much more on different areas of the planet, so we might see a decrease from where it was. Alright, so this is the NOAA satellite data from yesterday. 477 millibar reading, but when you go to the actual graph, it says 469 for the pressure. So the mean is 1878, or that's the average for this reading. The range is 1436 to 2378 parts per billion. The chartreuse color is from 2000 to the highest reading, 2378. So we can see a lot of this northern hemisphere is covered, is above 2000 parts per billion. So that's the morning. Here's the afternoon satellite, 1878 for the mean. The range is 1414 to 2412, so that's higher than in the morning. So we can see areas here over western United States and Canada, over the Pacific, and so on. Here's the METOP-2 satellite in the morning. Now this one is traditionally lower in the readings than the other one, and this one just looks thin. It like there's just so much data that's not there. Anyway, the mean is 1856. The range is 1386 to 2301 parts per billion. So again, a lot of areas in the northern hemisphere in the chartreuse color. And in the afternoon it was 1858 for the mean, and the range is 1461 to 2314 parts per billion. So I put that in the spreadsheet and added up all of those and divided them by 4, and we came up with the same reading as from last Saturday of 1867.50 parts per billion. So there was no change for this 477 millibar reading in the last week. So we can see a straight line on our graph here, meaning no change. So it's still 10.25 parts per billion higher than we started this in March, higher than that date. And 477 millibars is about 20,000 feet up in the atmosphere, or 6,096 meters. So there's that. So the highest reading we had was October the 12th at 1885. And now I'd like to just look at again. This is graph or chart graphic that was created by Sam Carana from arctic-news.blogspot.com. This is I'm going to start referring to this a lot because I think this is one of the best graphics I've ever seen of how he put together the potential rise in temperature from all the different sources because of all the self-reinforcing feedback loops and everything. So this is potential rise in global air temperature at land-ocean surface level from 1750 to 2026. So 2026 is not very far away, because in a couple of weeks it's going to be 2020. So that's only 6 years away. So here he has 2019. So he just lumped it all together from 1750 to 2019 for us to start with. Excuse me with my voice. I get hoarse from talking when I talk more than about 30 minutes. And we see this at 1.85 degrees Celsius. Here he has, by 2020, I'm going to just blow this up, by sometime in 2020, by the end of 2020, I didn't mean to do that. He anticipates that we'll be up to a 2-degree rise, the Celsius. And we've got, this is, so the pink is from up until 2019. So everything above the pink is after 2019. So he anticipates a little bit of the purple, which is the CO2 rise, a little bit of the green, which is falling away of sulfate cooling. Now this happens when we start cleaning up the atmosphere and you get rid of the cooling effect from the sulfates. So as we clean up the atmosphere, it's going to start getting hotter. And we've talked about that, and Guy McPherson talks about that too. And what else does he have in the mix? You really gotta blow it up to see. I think he's got some yellow and red in there too. Yellow, or this orangey color, is snow, ice, wind, and ocean changes. So it's warming from that because of we'd have less sea ice to reflect the sun back and all that. So that's going to heat up. And the orange is seafloor methane. So he does have a little bit of orange in there for seafloor methane to be affecting the temperature. So we're going to be seeing every year it increases exponentially from the year before, because it just builds on whatever happened the year before. So by the end of 2020, he anticipates a 2-degree sea rise. Here's 2021 with more colors in there because of all the feedback loops are building on top of each other. So by the end of 2021, it's not quite up to 3-degree rise, but it looks like about 2.75. That's going to be enough to really be affecting the whole planet adversely. And sometime in 2022, if his chart is correct, he's anticipating a rise up to not quite 4, so about a degree. It looks like from 2021 to 2022, it looks like up to about 3.75. And they say that with a 3-degree rise, that there will be no humans on the planet. We can't survive because we depend on the ecosystem. We depend on so many other factors, and all those things are going to be breaking down, and the planet can't adapt to such a fast change. So sometime in 2022 we will hit the 3-degree rise. That's only 2 years away. Seriously, that's only sometime in 2022. And we may hit it before then. I don't know. But at the rate we're going, it's not looking good. And we're going to start seeing huge impacts next year, and then the year after that is going to be that much worse. Look how much it rises in 2021. In 2020 it only rises 0.15 degrees, but in 2021 it's going to rise a whole bunch more. Or it could rise more. I don't think it's going to rise less, and I think Sam Carana's work is good. And see, here's the pink. Here's where he breaks it down, how much is each one is going to make it rise. And then by what year is that? By 2026, that's when it's off the charts. And it's going to be hard for anything to live here. I didn't mean to do that. So we have so much extra water vapor. That's the blue that starts coming in by 2022, because it gets so warm that it just builds up. And then the gray is clouds feedback, all the extra clouds. So it could rise. His worst case scenario is 18 degrees C or 32.4 degrees Fahrenheit. So we can't live in that. And I don't know what people are thinking, whether they think that the robots are going to run the planet and a whole bunch of transhumanism is going to happen, and the robots and AI are going to be here and, running the planet. I don't know. But organic life won't be able to stand it. So this is why I say time is short, and it's a lot shorter for a lot of people, for most of us, than for the rest of us. And I've got one more thing. Oh, and if you want to see that chart, you can go to his blog post, and he has that chart right here. This is from actually it first came out in February 2019. February 28th, 2019. A rise of 18 degrees C or 32.4 degrees Fahrenheit by 2026. And he says in the Arctic alone, 4 tipping points look set to be crossed within a few years. Loss of the Arctic sea ice's ability to act as a buffer to absorb incoming ocean heat. Loss of Arctic sea ice's ability to reflect sunlight back into space, or albedo. destabilization of sediments at the seafloor of the Arctic Ocean. That's what we were talking about in that paper. And permafrost melt. So I'm going to end it with a part of a video I watched. This is an interview that Peter Miller did with Guy McPherson back in November, and surrendering at the edge of human extinction. This was November 7th. And this is at the 1 minute and 16 marker. And they're talking about how long do we have.
Yeah. And several people have now concluded that the clathrate gun has been fired, that the methane bubbling out of the Arctic Ocean has reached an exponential increase. And so the clathrate gun, or the hydrate gun, those are clathrates of methane, that firing, and several people have concluded that that has occurred. Well, that's game over. You know, it's not game over today, it's not game over next Tuesday, but it's game over in the relatively near future. So, living...
All right, so there you have it. There you have it. So, and you don't have to have, you know, the 50 gigaton thing to go off. It can be coming up. It can be bubbling up, just like what we see here. It can be coming up all over the place. But specifically in the Arctic, here's what it's doing. That's total column. And here's surface level. And so we're in big trouble. Let's go back to Saturday. Oh, and one more thing. I've got carbon dioxide to show. Here's carbon dioxide. See, they don't have Saturday data, it's from Friday. Let's look at global. So it's darker than ever. And where we're at with carbon dioxide, latest CO2 readings, December 14th. This is the Mauna Loa Observatory. It was 411.66 parts per billion from NOAA. And this time last year it was 408.80 parts per billion. So, I mean parts per million. This is parts per million. I said parts per billion. Parts per million. So it's up almost 3 ppm since last year. So there you go. So things aren't looking good for the planet. We are in planetary hospice, and we're all grieving this, and we don't know what to do. We really don't know what to do. It's like, what do we do? How do we spend our days? Well, I recommend you get your spiritual house in order and be ready to go at whatever time that happens. So until next time, I love you guys, and I'm praying for everybody. So I'll talk to you soon. God bless you. Go in peace, and goodbye.